Hi, we're going to be getting ATP from a molecule of glucose and a molecule of fat. I'm briefly going to give a quick overview of both right here on this slide. Glucose is going to go through glycolysis, the citric acid cycle, and the electron transport chain. Whereas fat, the triacylglycerol, is going to be broken down to free fatty acids, beta oxidation to acetyl-CoA, and citric acid cycle, then to the electron transport chain. I'm going to start with glucose, or glycolysis, which starts with glucose, and the enzymes that are used in each. Start with hexokinase, which will give us glucose 6-phosphate. You see there an ATP is oxidized to give us ADP, and glycogen, which is the storage of glucose, so when we need to use our glucose storage, that comes from glycogen, and then it just starts in the glycolysis process. And then our next enzyme, glucose 6-phosphate isomerase, will give us fructose 6-phosphate. And then phosphofructokinase gives us fructose 1,6-diphosphate. Our ATP and another ATP is converted to an ADP here. Aldolase will give us 2,3-phosphoglyceraldehyde. And then tricephosphate isomerase will give us dihydroxyacetone phosphate. Glyceraldehyde 3-phosphate dehydrogenase will give us 2,1,3-diphosphoglycerate. And here we have NAD plus reduced to NADH plus H, which those will go to the electron transport chain. And then phosphoglycerate kinase will give us 2,3-phosphoglyceric acid. Here we get ATP now to ATP, and then phosphoglyceramutase to 2,2-phosphoglyceric acid, enolase to give us 2-phosphopyruvate kinase to give us 2-pyruvate, and we pick up 2 more ATP. Now, depending on if glycolysis is aerobic or anaerobic, determines the next step in this sequence. If it is anaerobic without oxygen, then we will have the pyruvate with the enzyme lactate dehydrogenase will give us lactate. If it is aerobic, those pyruvates will be going into the citric acid cycle. Aerobic versus anaerobic. Now we're going to go with the aerobic and going into the citric acid cycle. Now the pyruvate is outside of the citric acid cycle because really acetyl-CoA starts that cycle. So pyruvate dehydrogenase is going to come in and enzyme, and then coenzyme A will come in and we'll get acetyl-CoA. Also, we have an NAD plus reduced to NADH plus H, and then that acetyl-CoA will join with oxoalloacetate and citrate synthase, and the water comes in to give us citrate. Now our cycle is started. And we have aconitase, and then aconitase again, and then isocitrate dehydrogenase. We pick up another NADH plus H, then oxoallosuccinate. We pick up a carbon dioxide, alpha-ketoglutarate, and alpha-ketoglutarate dehydrogenase complex. Use another water molecule, get another NADH plus H, and another CO2. Succinyl-CoA synthase. We get a GTP here, which is similar to ATP. Then succinate dehydrogenase. We pick up an FADH2, fumarate, and we get a fumarase. Those on the inside of enzymes, fumarase enzyme, and water will give us malate, and then we'll have malate dehydrogenase. Pick up another NADH plus H, and then we're back to that oxoalloacetate, and the cycle can start over again with another acetyl-CoA. That's the thing about oxoalloacetate; it always ends it to join with acetyl-CoA. Now these NADH plus H's and the FADH2, those will be going to the electron transport chain, which is next. And this is important that you know that this is definitely aerobic. This is actually the final electron acceptor, and it requires oxygen. Oxygen is not technically part of this doesn't synthesize ATP directly, but without oxygen, this last part of the electron transport chain would not happen. So it does play a big role in determining if ATP is produced. And so here we've got, if you look at the chart, the long arrow is the electron transport chain, and through glycolysis we get two NADH plus H's that come this way, and then in that process of pyruvate turning into acetyl-CoA, we have two NADH plus H's, and then finally from the citric acid cycles where we get the most, we have 6 NADH plus H's and an FADH2, two of those, and that gives us our ATP. Excuse me. And then we have 32 of those, 32 ATP. That's our net from a glucose molecule in glucose metabolism. So net total ATP 32. And now this is where our glucose molecule, and those glucoses from carbohydrates are responsible about a third of our energy in light to moderate exercise, so it's fairly important. But now we're going to transition to our fat. Now our fat molecule, I talked about earlier, that triglycerol breakdown, and how that's going to work is we have our adipose tissue. If you look at the top of that picture, that's where our fat is stored. And now fat is can be 30 to 80% of our energy for biological work. So just knowing that, you can guess that our number should be larger for ATP. But anyway, that adipose tissue is our fat storage. It is going to be our hormone sensitive lipase is going to break that to glycerol and fatty acids. That glycerol, if you watch it, it goes down to glucose, to acetyl-CoA, to the citric acid cycle, and then in the electron transport chain. The fatty acid on the other side, it is going to be transported through the blood, and then in the blood it is prepared for catabolism. It will enter the muscle mitochondria, and then it will drop down, or through beta oxidation will be turned into acetyl-CoA, so it can go through the citric acid cycle and the electron transport chain. Now back to that beta oxidation here. In this chart you can see how the triacylglycerol is broken down to, again, we have glycerol and the 3 fatty acids. Glycerol goes over, and then fatty acids come down to the beta oxidation. The splitting of the 2-carbon acyl fragment, you can't really see that here, but so it's split. ATP is phosphorylates the reaction. There's water involved in this beta oxidation. Hydrogen passes to NAD plus and FAD. And this part you can see on the picture. If you look, the beta oxidation circle on the left part, that middle arrow, the acyl fragment joins a coenzyme A, and there's hydrogens that are coming off of that, and it forms acetyl-CoA. And from that acetyl-CoA, it goes into that citric acid cycle, and then there's 100. The net ATP from that is 147 from one molecule of 18 carbon fatty acids. Now, if you look at the picture here at the bottom, it says 460 ATP. That is, if you look to the left, that's 3 molecules of 18 carbon fatty acid, and we're looking at 1. So if you take that 441 and divide it by 3, you get 147. But like I said, that glucose for that carbohydrates is a third of the energy, and you had about 32 ATP, but that was light to moderate exercise. And now fat, 30 to 80% of energy for biological work, but that's going to be for more high intensity and more longer duration exercises, but it's 147 versus the 32. So we got to see that fat is definitely a major for storage for potential energy there. And here's some factors influence ATP production. We have diet. The low carb diets are skipping meals. Low carb diets are going to have low pyruvate production, and also low oxaloacetate production, which is one of the requiring factors in the citric acid cycle. So you've got to have that to have energy. So those things can affect ATP, which will give you low energy. Skipping meals, you're not going to be able to refuel or replace energy that's been used just from day-to-day things, and especially if you're doing intense exercises on top of that. Then exercise is going to affect the available oxygen. Electron transport chain requires oxygen for ATP to even be produced. Fatty acid catabolism is directly related to oxygen consumption. If there's no oxygen, the hydrogen stays with the NAD and the FAD, and that halts that process, so there's no energy, or not as much energy produced to really keep things going. But our low intensity exercises, more oxygen is going to be available, so you're not having to produce as much ATP to keep up. So that's going to be lower ATP production. High intensity, you're going to produce more ATP there, and that's where you'll really start feeling that from that fat storage is high intensity for long durations, and even the recovery of that. Dehydration, water, beta oxidation, citric acid, those required. I mean, if you remember looking back on the charts, those have water molecules in it. If you don't have water molecules to use because you're dehydrated, then that's going to affect energy levels or ATP production. And then you have temperature, and that's more of an extreme. Too hot or too cold, hyperthermia, hypothermia. Your enzymes are a major part of these processes, and those enzymes, if they're too cold or too hot, can be irreversibly damaged, and then they will not do their jobs, and then you won't be able to produce energy as effectively, or I mean, certain levels you just won't be able to produce energy at all, which would not be good. But that is what I have, and my stuff came from a textbook of exercise physiology, nutrition, energy, and human performance. And that's all I got. Thank you.